Woohoo! Welcome back. Today we're back with Berry-bacterium, and we're going to be modeling with exponential and logarithmic functions. In this first video, we're going to look just at exponential growth. Woohoo! Yay! So basically, there are two models of exponential growth that we use in this chapter and that are commonly used for sciencing. The first makes use of the concept of doubling time. So how long does it take for an amount of money or a population of bacteria, woohoo, to double in size? And because we're talking about doubling, our formula is going to involve the number 2. As before, n sub 0 or n naught is going to be the initial population. T is time, and that could be measured in lots of different ways. We have to be very specific in each problem to specify, are we talking days or years or millennia? And then A is how long it takes to double. Now, I made a note here, A and T must have the same units. So if T is being measured in days, A also has to be measured in days, and so on. So these two have to agree. Okay, let's try a problem. So a certain culture of bacterium, yay, initially has 10 bacteria and is observed to double every 2 hours. Find an exponential model for the number of bacteria in the culture after T hours. Okay, this is so nice and simple because we've got this formula. And as long as we understand what each of the parts means, we can rewrite our n of t as we need our initial population initially has 10 bacteria. So we've got 10. N sub 0 is 10. And then we've got the number 2. So a lot of times people put the 2 in parentheses, or you can put a multiplication sign, whichever you choose. I'm going to move Barry up here. Pardon me, Barry. There you go. Okay. And then my exponent, I'm going to leave the t as my variable, and I'm going to divide by 2 hours. So this means that t is the number of hours, right? Because I've got t hours and every 2 hours, and that's going to be really, really important. So then we're supposed to estimate the number of bacteria after 5 hours. So again, 5 hours matches the doubling time, hours. So we're not suddenly switching to minutes or days. And we're going to round to the nearest whole number. Okay, let's estimate using this formula. So in this case, 5 hours, n of 5, is going to be 10 times 2 to the 5 over 2. Now notice that it's not going to have a complete cycle of doubling. So 5 hours means every 2 hours. So 2 hours, it doubles. 2 hours, it doubles. But then we only have 1 more hour, so it's not going to quite double. So we're going to have to see what this would be equal to. Okay, so we can also write this as 10 times 2 to the 2.5, if you'd rather write it as a decimal. Okay, let's get out our handy dandy calculator. Woohoo! Move this a little bit sideways. Ooh, pardon me, Barry. I'm going to move you over here. Woohoo! Try to avoid the lights. Don't go into the light, Carol Ann. Okay, here we go. Okay, so I'm going to go ahead and try this. So I am old school. I'm from the time when calculators got really mad if you tried to do too much at once, but let's see if we can do it. So I'm going to do 10 right there. Oops, where'd it go? There. 10 times 2, and this is my exponent key here. You might have an x to the y or an x to the box. And then I'll raise it 2.5. Now, before I hit enter, let's think about what we're thinking. So after 2 hours, it'll double. 10 goes to 20. Another 2 hours, it doubles. 20 goes to 40. And then if it were to go another 2 hours, so if we had 6 hours altogether, it would go from 10 to 20, from 20 to 40, and from 40 to 80. But it didn't quite get that far. It's not 3 full doublings, it's only 2 doublings. So we're going to have to see what this is equal to. So let's give it a guess. And there you go. It's 56.5685, etc. So it's between 40, which was 4 hours, and 80, which would have been 6 hours. But it's not exactly halfway because exponential functions aren't linear. So there's kind of a scooping shape. So it isn't quite halfway between 40 and 80. Okay, so I've got 56.5685 and some other stuff. That's the exact value, right? I'm just writing down some of it. And then it says to round to the nearest whole number. 56.5 is going to round up to 57 bacteria. Now, to be honest, I don't know if you can count 57 bacteria or if when you've got small numbers like that, you count more in weight or volume, but we're going to go with it. We're guessing there's 57 bacteria in this cute little petri dish. Yes, I know it's a lovely little petri dish that's nice and close to all the best schools, and Berry Bacterium is very excited about it. Okay, so now's when, oops, don't sit there. Now's when things get really exciting because we're not going to be plugging a number into T. We're going to be finding out what is T after how many hours will the bacteria count reach 5,000. So if the bacteria count is going to reach 5,000, that's going to take a long time because, right, 5 hours only got us to 57 bacteria. So this is going to take a bit of time. So Barry's going to have to, there's going to be grandchildren and great-grandchildren and all that fun stuff. So let's see how we work out this problem. So this problem is going to be, what we're going to do is we're going to set up the equation. Oh, I forgot. We know what the initial population is, right? Sorry about that. I got excited about writing out the formula. And the initial population is going to be 10. And so that whole thing is going to equal 5,000. So let's see if we can solve this. So first thing I'm going to do is there's that 10 times 2 to the something. I'm going to divide both sides by 10. Divide by 10, divide by 10. And I'm going to end up with 2 to the T over 2 equals 500. So the question is, 2 to what power is going to give us 500? And those of you who have been studying computer science at all, or you know your binary codes, you might actually already know the answer. It's not as high as you'd think, but let's go ahead and give it a try. How do we solve this? Well, the best way to solve this is to go ahead and take a logarithm of both sides. Now you can choose common log or natural log. I'm going to use common log right now because, I don't know, we don't get a chance to use it all that often. Now remember that when we have a logarithm, the nice trick is this exponent floats down in front, just comes down. Whee! And so we end up with T over 2 times log of 2, and that's equal to log of 500. Okay, let me come over here. So I've got T over 2 times log of 2. That's equal to log of 500. So far, so good. So I'm going to multiply both sides by 2. And I'll get T times the log of 2 is equal to 2 log 500. And then I'm going to divide both sides by log of 2. There's a lot of writing. You may want to take breaks if if your hand starts to hurt or if your eyes start to go all funny, take breaks, get a snack. Okay, let's see what we can get over here. Oh, there's a lot of light there. Do not go into that light, Carol Ann. Okay, so I've got up on top 2 times the log of 500. So 2 times, and for my calculator, I click on log first and then 500. Now I'm going to go ahead and enter. This is the numerator. And then I'm going to divide by log of 2. So you can split it up into 2 parts like that. And then I'm going to get 17.9315, etc. And it says round to 1 decimal place. So this is going to be approximately 17.9 hours. Oh my goodness, barely fit that in down there at the bottom. What do you think so far? Woohoo? Woohoo! Yay! Okay, so we have finished one problem. And so let's go ahead and go on to the next one. This was doubling time. We're going to do all of this again, except we're going to use the other common formula. And this is going to be, instead of using 2 for doubling time, we're going to use E. And E is really convenient. One, because, well, let's be honest, natural log is right there. So we have log base E on our calculators. And it's really nice. E does fit the shape of exponential growth really well. So it turns out it's a really good model for growth, examples of growth like this, of exponential growth, like bacteria. Yay! Okay, so notice that here we've got the number at time t is equal to the initial population, right? Or if you're doing a problem about money, this would be the initial amount of money. And then you have E instead of 2. And here it's a little different. Instead of t divided by the doubling time, we're just going to have E times RT. Now I know that's a little bit small, so I'm going to write a second version of it like that. So hopefully it's a little bit easier. I'm not sure if it's completely easier to read. R is the relative growth rate, and it's a percentage of the population, and it's written as a decimal. And so this is pretty cool. The way that we talk about this is how, if you're doing biology or if you're talking about physics, this is actually the language that's used. So it's pretty cool. We're actually doing actual word problems, not just like weird word problems that no one would ever need to do. This is actual work we could be doing in science. Woohoo! So, the initial bacterium count in a culture is 500. So now we're in the big leagues. Barry's brought 499 of his friends. And a biologist later makes a sample count of bacteria in the culture and finds that the relative rate of growth is 40% per hour. Okay, so find a function that models the number of bacteria after t hours. First thing, let's check. Relative rate of growth is 40% per hour, and we're talking about hours. So we have agreement. The relative growth rate and the time have to agree, just like with the doubling time example. Okay, so then we've got n of t. Then we need our initial population. And so it says right here, the initial population is 500. And then the relative rate of growth is 40% per hour. R is the relative growth rate as a percentage of the population. Okay, 40%, written as a decimal. So we've got to write this as 0.40. That's because 40% is written as 0.40 as a decimal. Okay, and then we multiply that times t. Okay, that's it. Again, these hopefully, there's a lot to remember, but the steps are pretty straightforward. So hopefully this doesn't feel quite so scary as word problems might normally have been. Okay, what is the estimated count after 10 hours? So now we're going to put in n of, we're going to double check. T is in hours, good. If it suddenly asks you for days or weeks, you're going to have to convert. So n of 10 is 500 times e to the 0.40 times 10. So that's just 500 times e 0.40 times 10 is 4. Okay, let me get my handy dandy calculator out. I am going, pardon me, Barry, I'm going to move you again. Let's see if I can put it here where you can see what's going on without getting too distracted by the light. I've got 500. Now I hit multiplied by, on some calculators you don't have to write the multiplication, it assumes it. Now to get to e to the x I have to use my second key, so I'm going to do second and then the natural log key which has e on top. And there I've got e to the 4th. I'm going to close that parenthesis and hit enter. And that escalated quickly. So after 10 hours, starting with 500 of these, it's actually after 10 hours, it's going to be, what is that? Let me come over here where I can kind of see it and write 27299.07502 and some other numbers. And I forgot to say how to round it, so let's just round to the nearest one. That would be 27299, so 27,000 bacteria, which is impressive. It started with 500 and it just escalated from there. And so the next question is, after how many hours will the bacteria count reach 80,000? It's a fair question. So let's go ahead and work on that one. And again, just like in the previous case, we're working with E as a base, but our general approach is going to be the same. So I want to know how many hours for n of t to equal 80,000. And just exactly the same way as with the previous problem, I'm going to write n of t is 500 times e to the 0.40t, which we want to be 80,000. Okay, first thing I'm going to do, you got it, I'm going to divide out the 500. I got to get the base by itself. The number in front of the base has got to go. So I've got e to the 0.40t is equal to, and I'm sure I could figure this out. It's going to be like 160, but let's double check. 80,000, 1, 2, 3, divided by 500 is 160. Yay! I've still got it. Okay, now either take the natural log of both sides or just convert to natural log, logarithmic form. I think the book likes to take the natural log of both sides, so we can go ahead and practice that. The point is, you've got options. Notice that over here, natural log of e cancels itself out. It undoes itself. And all I have is 0.4t on the left. And over on the right, I've got the natural log of 160. Now, it might feel weird. You can always write this as 4/10 and deal with it as a fraction. But I'm just going to divide both sides by 0.4. Let's calculate that. Oops, sorry. Sorry. Okay, so I'm going to get my natural log key, 160. And I'm going to hit enter, and then I'm going to divide by 0.4. And I'm going to get 12.6879, some other numbers. And again, it doesn't tell me how to round, so I might round to 13 hours. You could also round to another. You could round to hours and minutes if you like. So does this make sense? And I would claim it kind of does, because 10 hours got us from 500 to 27,000. So it makes sense that if it's going to every hour, the relative growth rate is 40%. So it gets another half, slightly less than half every hour. That makes sense. That's how I'm slowly going to get up to 80,000 hours. Or 80,000 bacteria. Sorry about that. Okay, woo! So, one more type of problem. And this one is the easiest to state, and I think the trickiest to solve. So I want to make sure we did an example of this one. So what's going on here? Well, in this case, we've got a problem that says if we observe the count in a culture of bacteria of 100, so at t equals 2, n of 2 is 100, right? And when t is 8, 10,000 after 8 hours. What is the relative growth of the bacteria population? And here's the thing. This is the problem that makes the most sense. So normally you would go into a situation, you wouldn't necessarily know the relative growth rate. You would just be able to measure how many bacteria, either is by counting or by weight or by volume, however you're going to do it. So you would compare these, and that would help you get the rest of the problem. So coming up with a formula this way, I think, is the most authentic example of what you would see in the real world, in quotation marks. So let's go ahead and see how to do this. There is a trick to this. And the trick is, look at the ratio of n of 2 over n of 8. So I know my n of t. I'm going to go ahead, since I'm talking about relative growth rate, that means I'm going to use the e to the rt formula, right? So that's when I've got relative growth. If it said doubling time, then I'd be using the formula that has the 2 in it. Okay, so n of 2 is going to be whatever the initial population was, e to the r times 2. And n of 8 is going to be the initial population, e to the r times 8. Now we know n of 2 is going to be 100. And we know n of 8 is going to be 10,000. And this is the trick that we use all the time in math, is when we know two different pieces of information like this, we're going to take the ratio. So I'm going to look at n of 8 compared with n of 2. Now, what does this allow me to do other than make a fraction? And I know you're all like, seriously, why do we want a fraction? And the answer is because, and here I'm going to rewrite it as 8r and 2r, because I'm going to be able to cancel things out. I'm smushing these two pieces of information into a single expression here so I can compare them. Okay, so what's the first thing that happens? Well, the first thing that I see is my n sub zeros, my initial population, doesn't matter anymore because we're comparing these two times, 2 and 8. So what happened at time equals 0 doesn't matter. So I've got e to the 8r all over e to the 2r. And then over here, and if you don't know this fact, you can always check it out. 10,000 divided by 100 is 100. So this isn't too bad. And then one more step, and I know it's very tempting to multiply both sides by e to the 2r, but let me remind you that e to the 8r divided by e to the 2r both have the same base. We get e to the 8r minus 2r. Or in other words, e to the 6r equals 100. So it's a pretty neat trick if you take the ratio, and I just encourage you, just try to remember, we're going to take ratios to compare things. Suddenly the initial population cancels. Suddenly the two expressions involving E can be smushed into one expression. And then our last step is, right, whenever we've got an exponent that we want, we take a natural log, or any log, really. Natural log is nice because natural log and E, remember, they undo each other. So I get 6r equals natural log of 100. Or I can divide both sides by 6. And I get r equals natural log of 100 all over 6. And I could leave it like that, but let's go ahead and figure out what it's equal to. So right here, natural log of 100, close parenthesis, divide by 6, is going to be 0.767528 and some other numbers. So it's about 0.77 or 77% is our relative growth rate. So that's how fast the population is getting bigger each hour. So each hour, we're gaining another 77% in the relative growth rate. Okay, woohoo! Congratulations! You made it through a very long video. Go take a break. The next video is going to be all about radioactive decay. So that's going to be super fun. We're going to be talking about half-life and radioactive decay. Woohoo! So until then, go do something fun. Know that you're amazing and incredible, and I'm so proud of you, and I'm so glad you're working so hard. So thank you for watching this. Math on and woohoo!